Today I'd like to show you the speeds of the Earth as it moves around its orbit and as it turns around its axis. The orbit of the Earth is this circle. This is where the Earth is rotating around the Sun, and we know very well that for one full circle, for one full revolution, it takes 365 days and a quarter. The word actually revolution comes from Nicholas Copernicus in 16th century, who in his work the revolutions of the planets, he invented and he introduced this word. Later it was taken by the social and political and historical sciences as a changing of a government, revolution. But the original meaning is the turning of the planet around its star, around the Sun. So now we know that the Earth is moving around the Sun, right, for 1 year. Is moving. You can see also the inner planets, Mercury and Venus. The Earth is turning around the Sun. So now we need to check up how can we find the speed. Now we know very well that the distance from the Earth to the Sun, that's measured long time ago, and you can check it up even in antiquity. They were able to check it up, not with the same accuracy that we check it up today, but they were able to check it up. How did they do that? You can check it up. You can find out. So that's firmly established, and it's 150 million kilometers. Because kilometer is not a standard unit of measurement, the standard unit is a meter, we're going to turn it into meters. So it's going to be 150 billion meters. It's the distance between the Earth and the Sun. So how can we find now the speed of the Earth on its orbit? Okay, what we do, as I always say to my daughter when we do such problems, what we know, what we don't know, and how we're going to find it. We know the distance. How we're going to find it? We also know that we can find out the orbit by applying the formula, by multiplying the radius, which is 1.5 by 10 to the 11th power, because it's 150 billion. Okay, we need to multiply this to 2 pi. So we do this, 2 pi, and we found now what is the length of the orbit. This is the length of the orbit for 1 year. This is how many meters the Earth is turning in 1 year. Now let's check up how many meters is turning in 1 day. So we divided this because 1 year has 365 days, 365.25, and we're getting for how much is for 1 day. 2.5 billion meters. Okay, let's check up for how much is per hour. Divided by 24 hours. We've got it. So it is 107,000 kilometers per hour. 107,000 kilometers per hour. All right. That's 1,000 times more than what we normally travel on the highways. 107,000 kilometers per hour. Let's check up for a minute. 1 hour has 60 minutes. We divide it by a minute. Okay. So for a minute, we've got 1,800 kilometers. This is for 1 minute. Right. And for a second, 1 minute has 60 seconds. We can see it's 29,000 meters, 29,800, or we can say it's 30 kilometers per second. 30 kilometers per second. This is the speed of the Earth in its orbit. So every second the Earth is moving 30 seconds. Can you imagine now if you could have jumped, right? And the Earth is turning around you. So you go from Durban to Joburg, which is say approximately 500 kilometers. It's going to take you approximately 17 seconds. Can you imagine to do that? So this is the speed of the Earth around the Sun. But also, as I said, the Earth is not only turning around the Sun, but is turning also around its axis. For 24 hours, it's making a full turn around its axis. This is why we've got day and night, day and night, day and night. So now, let's find the speed of the Earth around its axis. You'll be surprised to know that the Earth is not turning with equal speed, linear speed we're talking, in all its points. It's turning with the highest speed on the equator and with zero speed on the pole. Right, and we're going to show you why. Now, we know that the Earth radius is 6,370 kilometers, or 6,370,000 meters. We said we're going to use standard units, the meter. Right. So this is the radius of the Earth. Okay, this is the radius. So what we're going to do now, we're going to find the circumference of the Earth. 6.37 by 10 to the 6th power. Right? We need to again multiply this by 2 pi. By 2 pi. And we're going to see now the circumference of the Earth. You can see it's 40 million meters, or 40,000 kilometers. So that means from the pole to the equator, it's 10,000 kilometers, and actually this was the definition of the meter. 10 million meter is from the pole to the equator, and actually the definition of the meter was 1/10 millionth of the distance from the equator to the pole. We found how much is the circumference of the Earth. So now we need to find again at what time the Earth is taking this distance. We said 24 hours. All right, 24 hours. So we divide it by 24 hours. She's taking this distance. And we've got 1,000,000.6 meters in 1 hour. All right. Now let's check up for a minute divided by 60, because 60 minutes in 1 hour. We've got 27,000 meters in 1 minute. Let's check up for a second. We've got 463 meters in 1 second. That's on the equator, but on the pole, the Earth is not turning. It's just going around, with around its, because the axis is there. So on the pole, there is no speed. Look, all around, the angular speed, that means how many degree per second, is the same. but the distance traveled, the linear distance, is not the same. It's 463 only on the equator. So how can we find it, say, for example, in Port Shepstone, which is here? Okay, here is a Port Shepstone. Now, so what we do, there is Port Shepstone. Now, we know that now this place is not rotating the same speed as in the equator. It's slower. You can see it. Right. So now how can we find the speed? It's very easy. What we do, we know the speed at the equator, but we know also this angle where Port Shepstone lies from the center of the Earth, of the equator. How many degrees? What is actually the latitude? What's the degree Port Shepstone lies from the equator? So now we've got 463 meters. That's per second, the speed. Now, need to check it up how we can divide it. Obviously, this is cosine. So now we see this right triangle where you can see the hypotenuse of this right triangle and the adjacent. So the angle is actually the angle of the latitude. Actually, at what geographical latitude is the place that we're going to study, say Port Shepstone or any other place on the Earth. So now the cosine is the relation between the adjacent and the hypotenuse. We divide the adjacent to the hypotenuse, and then we can see what's the relation. So by knowing of the latitude, that means the angle, and one of the two, the adjacent or the hypotenuse, then we can find the third one, because by the formula cosine equals adjacent divided by hypotenuse. So now if we know the angle, right, and we know the hypotenuse, so we can find what is the size of the adjacent, and then after we can find actually what is the speed by multiplying the cosine of this angle to the speed which is on the equator. Very easy. So we do it. Okay, so let's multiply it by cosine. What's the degree we set? The latitude of Port Shepstone? It's 30 degrees. So we put 30 degrees here. And we've got that the speed is slower. You see, it's 400 meters per second. See, that's a different story. So now, if you don't believe me that on the pole the speed is 0, okay, that's a southern pole, same is with the northern pole, we do the same multiplication. (463) by cosine of 90 degrees, 0. You see, on the pole the Earth is not turning. Now let's check up somewhere in Canada. Say here. Got this triangle. So again, we get the cosine of the angle of the latitude. And the cosine, we know it's adjacent divided by the hypotenuse. Right. Since we know the hypotenuse, and since we know the angle, we can find the adjacent. Very easy. So, 463 again by cosine of, say, 60 degrees. Say this angle here is 60 degrees. 231 meters per second. This is, you see, it's half of this speed, because cosine of 60 is 0.5. So it's half of the speed if we are in this latitude here in Canada. Now we found that the Earth is rotating around its axis on the equator with the speed of 463 meters per second, higher than the speed of the sound. All right. Now we found also that if we're in Canada, anywhere on 60 degree latitude, we're gonna be moving with half of that speed. It's gonna be interesting to find out, is there such a place where we can, with walking, move with the same speed. That means we're gonna walk together with the sun. Let's check it up. Now, how can you find out? Okay, we know that walking speed is 1 meter per second, or 3.6 kilometers per hour. Okay, so now this 1 meter per hour, we need to divide in order to find in which place of the Earth, in what latitude we need to be. We need to divide by the speed at the equator. So we divide it by 463, and we're getting this number. All right. So this number we save, and we're getting inverse cosine. So we're putting it there, and we're getting the geographical latitude. This is 89.87, almost near the northern pole. So now 89.87. Let's see if we can turn this in kilometer, approximately in kilometers. So now 90 degrees, we say it's at the pole, but we're not right at the pole. So now let's see. This is how many degree from the North Pole? 0.12 degree from the North Pole. And we know that in 1 degree we have 111 kilometers approximately. So we need to be 13 kilometers from the Northern Pole so that our walking speed matches the speed of the Earth. You see, that's how it is. Now, let's see this 463 meters per second on the equator, if we can convert it with kilometers per hour. We multiply by 3.6. And we're getting 1,666 kilometers per hour. Now, if we use fighting jet like a F-16 or a MiG-21, they develop a speed, maximum speed about 2,170 kilometers per hour, much higher than 1,666 kilometers per hour, which is on the equator. So now if we travel with these jets, you can actually move with the speed faster than the speed of the Earth. If we travel with this jet westward, we will be able to see the sun actually turning the other way. Instead of the sun going from east to west, the sun is going to turn from west to east. So if we start traveling, say, by sunset, we're going to see the sun, instead of going down, is going to go up from the west. There is a video on a Google. You can check it up, and you can see it by yourself. For those that use miles, 1,666 kilometers per hour, it's 1,000 miles per hour. So now you can check it very easily. What is the speed of the Earth at your place? Very simply, by multiplying the speed of the Earth on the equator by the cosine of your latitude. Very easy. And I challenge you, you can do it. You can see what's the speed. Thank you for watching this video. I hope it clarifies to you how we can measure the speeds of the Earth around the Sun and around its axis.